for thanks for inviting me for this colloquium and sharing the work that we are doing with MeerKAT telescope. And I will also show that how we have effectively used South Africa Large Telescope SOL to design this large project with MeerKAT. And I'll first go ahead and share my screen. Are my slides visible now? Would someone confirm,
Yes,
please?
yes,
And I'm also clearly audible, right?
yes.
Okay, great. So I'm going to give an overview of MeerKAT Absorption Line Survey, and it's a large project running on MeerKAT telescope. Uh, Formally, it has been awarded 1655 hours of time, of which 1300 hours have been completed over last 4 years, and we hope to finish observations later this year. And I'll show you that we have already made several data releases related to radio continuum images of sources in the sky and various spectral lines that can be detected in the radio band. And as I was mentioning, I will in particular spend a couple of slides on demonstrating how we effectively use SALT to design this survey in the early stages. So MeerKAT telescopes requires no introduction. It's the most sensitive telescope at centimeter wavelengths, and it's situated in South Africa. And remote location reduces the impact of radio frequency interference. And on the right hand side here, we can see how the array configuration is. So it has got centrally concentrated array distribution, which means that it has got very excellent surface brightness sensitivity. And as part of MeerKAT absorption line survey MALS, what we are trying to do is to do a blind search of H1 21 centimeter and OH 18 centimeter absorption lines. These two lines are uh, very nice traces of cold atomic and diffuse molecular gas in the interstellar medium, and that's the basic reason and for targeting these. And we are using L band and UHF band on MeerKAT for these. These two bands run from 900 to 1670 megahertz and 580 to 1015 megahertz. And if we use them both together, then for a particular portion of the sky, we can actually cover redshift range 0 to 2 uh, is uniformly to search for these spectral lines. And instantaneous bandwidth at MeerKAT telescopes gives a 5 kilometer per second spectral resolution over the entire band, and that's also very excellent. And I will, in subsequent slides, demonstrate that why these specifications are very good for doing this kind of survey. And as you know, MeerKAT is now currently undergoing expansion, and eventually it will get incorporated into square kilometer array later in the decade. And this is a basic timeline of the survey. And here on the top of the slide, I give some of the basic specifications. What we are trying to do is to observe about 400 pointings over the sky and at a spectral resolution of 6 kilometers per second. And we aim to reach a spectral RMS of zero point 0.7 millijansky per beam at this spectral resolution. And the idea is that to get uniform sensitivity across the band, so we integrate at L band for 56 minutes and at U band for 120 minutes. And that's because at U band, the system temperature is somewhat higher, so we need to integrate a little bit more to get to the same spectral RMS. So around 2017, we started commissioning and science verification. I will show some results from that later in my presentation. And we started survey in June 2020. And as I said, as of now, we have completed 1300 hours of observation, 18% of the observing time approximately, and which implies that for L band, we have observed all the 400 pointings, and for U band, we have observed about 300 pointings. And most of these are also processed, and later this year we expect to complete observations. So total survey volume, if we talk about terms of data, is about 8 petabytes, and this includes all the raw visibilities as well as the processed data and spectral and cube. So it's also a significant big data challenge to progress this survey. So what's the primary objective? The primary objective, as I was saying, is to do a blind search of H1 21 centimeter and OH 18 centimeter absorption lines. And what we are trying to do here is to understand how neutral hydrogen in the universe goes into cold neutral medium phase and molecular hydrogen. And through that, if we can understand how the star formation rate density in the universe is evolving as a whole. So this slide demonstrates what the primary objective is on left-hand side, you can see the rapid evolution star formation rate density over redshift range 0 to 2. So this is the reason that through MALS using L and U band, we are targeting this redshift range because this is where we see the most rapid evolution star formation rate density. And the idea then is to understand that through 21 centimeter OH lines that how this basic fuel of atomic and molecular gas is actually getting into the galaxies and converted into stars. So if we can map this, we can get a better understanding of some of the underlying processes about how this rapid evolution is taking place. So why would we want to do this as radio? Because cold gas is also associated with dust, and radio wavelengths being longer compared to say optical or ultraviolet are naturally unbiased against dust. So radio window is naturally the most effective place to carry out such an exploration. And how do we do this using absorption lines? So this is illustrated here. If we look at top of the slide, we have a distance background source. This could be a radio source in the radio window at the left. And as the light traverses through the universe and reaches an observer at the right-hand side, then the light from this bright object will actually carry imprint of whatever material that has been in between. This could, to start with, can have emission lines coming from this bright radio source itself. In this case, it's an AGN. And if we look at here, the spectra, this is actually an optical spectra to give you a better feel for how this kind of radiative transport takes place. You would have these emission lines coming from the AGN itself. But in addition to this, one will also have these large number of absorption lines on the left-hand side. These are low column density uh, absorption lines corresponding to lamellar alpha forests in the universe. This is the intergalactic medium. And then on the right-hand side, we see these deep, narrow absorption lines that are actually coming from material that may be associated with the galaxy or could be associated with the uh, uh, intergroup medium as well. So, and these correspond to not only neutral hydrogen, but also various metals that are present in the galaxy. So by taking an spectra of one such sight line, we can study a lot about intervening matter or the distant galaxies, which wouldn't otherwise be detected because they're too faint to be detected in emission. But if we take large number of such spectra, we can actually build up a general picture about how the galaxies are evolving as a whole, the galaxy population as a whole. And that's the basic idea demonstrated here in the maths. I don't want us to understand this maths in detail right now because that would take quite a significant amount of time. But if you look at this particular equation on the right hand side, it consists of like two important parts. One is this underlying cosmology, which is like corresponding to 1 plus z square, and the denominator here, that's, let's say, we are not interested in right now. What we're interested here in is the G term here, which actually contains the optical depth and the redshift coverage that a telescope can provide. So better are these two terms, which means that at very high survey speed, we can actually cover large redshift range and also be more sensitive to the low column density or warmer gas as well. And for that, so what we need to do is to be able to use a telescope which provides instantaneous wideband. That's what MeerKAT is, and also which has a large field of view, so that we can not only look at one source at a time, but within a field of view, it is sensitive enough so that it can provide spectra towards large number of sources. That way, we can detect large number of such sight lines with good optical depth sensitivity, and that will, using those hundreds and thousands of those, then we can actually build a picture about like how the galaxies at a particular redshift range are evolving uh, in this case. And with MeerKAT, what we will be able to do through this survey is to observe 10 to 100 times more such sightlines that have been done in the past. And that's the basic idea, that why MeerKAT Absorption Line Survey can provide a step forward in understanding the distribution of cold gas around galaxies using this project. So what's the Mars footprint, right? What portions of the sky we are looking at? That's always an important question when we are trying to uh, look at the sky to address any astrophysical problem. So in this case, what we have done is that we have identified 400 pointings, which are centered at radio sources better than 200 millijansky, because we select each pointing at a bright radio source, because this sightline then probes low column density gas because it is very bright. But then there are also serendipitously many fainter sources in the field of view, and through this we can uh, observe gas which is at higher column density. But a combination of this bright and fainter radio sources can actually sample the entire column density distribution. So that's the basic idea. But how do we select these bright radio sources in the sky? So this is showing such example pointing from our survey. So this is actual MeerKAT image that has come out. At center, there's this bright radio source, and there's this large number of numerous sources that we have detected. Each pointing actually has about 4,000 sources, but of these, only few hundred are bright enough to provide sensitive detections of absorption lines. And on the right-hand side, what we are seeing is that actually RMS is increasing as we go away from the pointing center, and that's just the natural response of the beam of the telescope. So that's the kind of radio continuum view that we get using this survey. And when we use the entire sensitivity of the wideband, we get a sensitivity of about 15 microjansky per beam. But when we use the spectra at the highest resolution of 5 kilometers per second, then we have a spectral RMS of 0.7 millijansky per beam. And in terms of H1 column density for 100 Kelvin gas, this implies sensitivity to detect 5 times 10 to 19 per centimeter square, and that's towards the central source. And as we go towards fainter sources, it's like higher column density that we are talking about. This is how the survey footprint looks like in the sky. Each red circle here represents a pointing that we are observing and we would like to observe. And at L band, as I said, 400 of these we have already observed. And so when we were starting this project, and this is of course like MeerKAT being in southern hemisphere, we wanted to identify suitable pointings that can be observed. For that, we wanted to know what are the redshifts of these bright radio sources in the southern hemisphere. And as we know, like now, more and more optical surveys are happening, and they are also covering a southern hemisphere. Especially in the next few years, with foremost on ESO telescopes, we would have a very good spectroscopic coverage in the southern hemisphere. But when we started planning MeerKAT Absorption Line Survey, there was hardly anything in the southern hemisphere. Of course, Sloan Digital Sky Survey existed in the northern hemisphere. So what we did was that we identified a large sample of like 500 to 600 radio sources in the southern hemisphere, which could be potentially observed as part of MeerKAT Absorption Line Survey. And we carried out a large spectroscopic campaign using SALT telescopes. So we used something like 180 hours on SALT telescope during 2015 to 2017, and observed more than about 300 radio sources, very bright radio sources. So on its own itself, it was a very unique project, because such bright radio sources are rarely observed as a sample to obtain uniform spectra as such. So we obtained these spectra, measured redshifts, and all these spectra are now publicly available. People can use it, and these are all published, and it allowed us to explore how the properties of various absorption lines detected in optical wavelength using salt spectra are evolving. What are the black hole masses associated with AGN in these powerful radio sources? What is the statistics of broad absorption lines detected in these? So all these results are explorations have been done and are published. So this is one major output that came out of this project that was observed with SALT. And now we have carried it forward. We have obtained now better spectra with Magellan and VLT for these objects, and better statistics is coming out of those as well. So this is how SALT contributed to actually through this large program to the design of this survey. So once that we understood that how these pointings are to be selected, particularly to carry out this survey, we started observing with MeerKAT in around 2020, and each integration, 1 hour integration at L band contributes to one terabyte of data. So for the entire survey volume, this corresponds to 1.5 petabytes of just the raw visibilities. So to overcome this data challenge, we have set up a large data processing facility here at IUCAA. It's a computer, it's a cluster consisting of about 25 nodes, and each node having about 400 gigabytes of RAM, and it is complemented by a multi-temperature like archive of 8 petabytes. Like the fastest storage is like of 4 petabytes, and the rest of it is the archival storage to store data products. I cannot go more into the details of how this data processing is done, but we have basically set up an automated data processing pipeline which is tied to our cluster and processes this data automatically from starting from visibilities. Visibilities are brought from South Africa to here in tapes. So every couple of quarters, when the observations are finished for 50 to 100 pointings, we collect all those data on tapes and bring them over to IUCAA, and then they are loaded onto our cluster, and then these gets processed automatically to generate the kind of spectra that I will show, and an example of wideband continuum image that I have already shown. Because for these kind of projects, we cannot really do actually a manual data processing. This showing some kind of an example of a clean interface of our processing pipeline. So through this, actually, any team member situated anywhere across the globe having access to internet can actually process data without actually directly logging into the cluster itself. So that makes it very convenient also to bring in all the expertise of team that is distributed across the globe. This is a view of like how the data passes through calibration, spectral line processing. A part of the processing chain generates wideband continuum image, another one splits this wideband spectra containing 32 spectral line channels into smaller chunks of about 50 to 60 megahertz and generate spectral line cubes and spectra out of those. So in total, like we are generating close to like 100,000 spectra for the entire survey, and they are split into like 15 to 30 spectral chunks. So we are talking about dealing with like just the spectra. Then we are talking about dealing about a million spectral chunks in this case, which then have to be processed through an automated spectral line search to detect spectral lines itself. So it's a like end to end. If we are looking at, it's an entire big data processing challenge, which actually requires compute of about 3 to 4 years on the cluster that I described. So this is a brief summary of what I have talked about. I have presented to you what the survey footprint looks like and how we use SAAO to define the survey footprint. And then also I have given you a flavor of like the kind of big data challenge that we need to plan for to generate all the data products that will be used for the survey. And our eventual goal is to make all these data products public to the community. And we have already made some data releases that I will talk about. So these can be accessed over internet by anyone, and people can carry out their favorite research uh, using these. So let's talk about science and data releases. That's what will be the focus of rest of my talk, and I intend to finish in about 15 to 20 minutes so that we have some time for discussion here as well. So this is the first spectra that we took. It gives you a flavor of like how a particular spectra will look like taken with both UHF and L band. So this is a sight line. You can see in the first panel here, it corresponds to UHF band starting from 560 megahertz down to 1060 megahertz. And the next two panels are showing spectral coverage that comes from the L band that is running from 870 megahertz to 1670 megahertz. And then there are some blocks that are marked here. That's where we have strong radio frequency interference. But you can see like by and large, there are large chunks, especially in the UHF band, which are like completely devoid of RFI. This particular sight line was chosen as our first target because it already had a couple of absorbers detected towards this, which are marked here as circles in this case. And the idea was to sort of observe this and do a science verification to understand like how well we are actually doing in terms of required sensitivity for the project. So when we got this, since MeerKAT is like more sensitive than anything that existed before at these wavelengths, we not only confirmed the validity of these known lines, but we also detected some of the new features which were not seen before. These are very faint lines of OH that were not detected before this sight line, which has been actually detected around for 30 years. It has been observed at various other telescopes for science verification purposes like we are doing here. But since MeerKAT is so sensitive, we ended up detecting these new features from the science verification itself. We also detected even much fainter radio recombination lines from this sight line. In this case, this is not direct detection. They are about 20 transitions of different recombination lines across the L and UHF band, we were able to stack them and detect this feature. So this is giving a nice flavor of like how we can actually use these widespread spectra to not only detect lines of H1 and OH, that is the main goal of the survey, coming from the neutral cold gas, but can also detect signatures that are corresponding to this ionized gas, which actually is not detectable as well. So once we take these wideband spectra, then there is a whole range of science that becomes possible. And in over next few slides, I'm going to show you some of the different science that we have done over last couple of years. So what we are seeing here on left hand side is a field that has been observed with MeerKAT and also observed with Hubble Space Telescope and Magellan and VLT News as part of a CUP survey, which has an overlap of about dozen pointings with MALS. And at the center of here is a QSO in this case as well. And then if you zoom in on this in the second panel, we see that there is this QSO, but then there happens to be these two dwarf galaxies here as well, right? And they have been observed with Muse on VLT to get IFU spectra as well to observe H alpha from this, for example. And then if you look at it, we don't really see anything very interesting, but since MeerKAT is so sensitive, in just 1 hour of integration with L-band, and these galaxies are close enough that we also detect H1 emission in 21 centimeter line from these galaxies. And when we look at these, we can see that these two galaxies are actually embedded in this filamentary structure of H1, and they are interacting with each other. And this towards this quasar sightline, we detect a deep laminal alpha absorption here. So through this kind of combined observation of 21 centimeter emission in H1 here from radio, and then absorption coming from laminal alpha and absorption constraint also coming from MeerKAT, we can actually not only constrain the thermal state of the gas, but also we can determine what is the origin of the gas here that we are seeing in absorption. And this is something which we will not be able to tell otherwise, right? Because just by looking at this quasar here and the sightline in absorption, we cannot tell anything where the gas is coming from. But in this case, we can say that like this gas is actually corresponding to this extended H1 disk, which has been further actually stripped from this extended H1 disk by interaction in this case. Right. This is another example. Now I'm going to very high redshift. This is now UHF band spectrum, redshift of 1.3. So it will correspond to about 580 megahertz. And there is this beautiful absorption detected in 21 centimeter line, which we see in this panel here. And top is the radio continuum image. But when we look at its optical spectrum, which is shown here in the extreme right, we find that there is no signature of any absorption here at the optical wavelengths. Some of the features that we are seeing here in the spectra in optical and UV are corresponding to different transitions. They are not associated with this quasar at all at this redshift 1.3. So let's not get be distracted by them. So what we are seeing here is that actually when we look at a radio spectra, it is showing large amounts of cold gas associated with this AGN. But when we look at the optical spectrum, we do not see anything at all. And to some extent, this can be explained by misalignments between radio and optical sightline, because we know that radio sources can be more extended. But a bigger question can be answered by looking at such objects through a blind search from MALS is that how many such absorbers which we may have missed in the optical surveys, and that can tell us something more about the immediate environments of these powerful radio sources. So now I'm talking about large data releases that have been done so far, and these are publicly available. So our first data release consisted of L-band continuum images, and this here we detected 500,000 sources. So in this data release, we first focused on images that came out of smaller fractal chunks across the L-band. So this resulted in images with sensitivity of about 20 to 30 macrojansky. So this is still factor of 2 to 3 higher than what the entire wideband sensitivity will be. We took this approach because we wanted to first get continuum images and spectra of the smaller chunks, because those are exactly what we need for the entire spectral line science. And these are at a spatial resolution of 8 to 12 arc second. And through these, we were able to determine source counts across the band down to 100 microjanskis. And also, we were able to test how the spectral indices of radio sources across different populations may be evolving. So this provided us also a measure of the validity of how the survey as a whole and the data processing in general is performing down to the sensitivities of what is needed for the MeerKAT absorption line survey. So this is, we could say that like not only a new output coming out of the project, but also providing a verification down to the sensitivities of where the uh, uh, survey should be to be able to achieve all the goals. So these are publicly available and that can be used. And this slide shows how different radio surveys have progressed starting from 1940 and starting from Rote-Reber's some of the first observations. And then if we go towards right, we have all these different large surveys which are actually targeted to do much deeper radioconform imaging, much larger radioconform imaging of the sky, like EMU, LOFAR surveys, and VLAS are running on VLA, and then TFI GMRT survey that's at 150 megahertz running on completed on GMRT. So this is where MALS sits. So we are talking about MALS L band detecting about a million sources, and that's what our second data release was, where we used the entire wideband sensitivity. So you can see that we are actually getting into the regime where most of the new competitive surveys are performing. So this means that we can potentially use MALS because it covers a somewhat different parameter space to address various astrophysical issues related to radio sources through its quantum images as well. And this may be of interest to some of you here in the audience. And one of the things that we did using these deep images was to ask the question that now we have got these 400 sources distributed across the sky. Is the source distribution in these 400 pointings consistent with what we see as the cosmic radio dipole, right? We know from the CMB maps that we do find an excess dipole motion here. What it shows here is that like we tend to be moving in this particular direction, we as in solar system, right? And we really don't understand why that should be the case. And that's the discrepancy that has been observed by most of the previous radio and optical and IR surveys. And what we found from our measurement is that we can actually we are consistent with the CMB dipole in this case. There's no discrepancy as such, but this of course such an important question that we are going to test this again when we get our UHF images, and there's something that should be done with other large area surveys as well, and eventually with the square kilometer as also, right? And so now moving into the spectral line science. So as I was describing that with MeerKAT, we are able to cover using both L and UHF bands starting from 580 megahertz down to even or up to 1670 megahertz. So this means that we are also looking at frequency it's around 1420 megahertz and 1670 megahertz, which means that we can actually look at H1OH from our own galaxy itself. And that's an important thing to do also because uh, for the simple reason that when we try to understand how the cold neutral medium or warm neutral medium in external galaxies is distributed or evolving, we are always talking about these comparisons or this big picture in the framework of what we see in our galaxy, because that's where we can study these distributions of these gas in most detail, their structure in most detail. So continuously we need to be able to update models in our galaxy using better data. This is exactly what we have done. So there was two objectives of carrying out these exploration with MeerKAT data. One is that we wanted to test how our methods for blind spectral line search will work on galactic in the galactic frequency range, because it's the only frequency range where we don't have any significant external RFI. So that's one thing that we wanted to test. And second thing was to use these high quality data to actually understand how we can actually uh, understand the distribution of cold and warm gas in our galaxy itself, and then using this improved model to then further predict whatever that we will see in the external galaxies. So when we did this, we actually were able to get very high sensitive spectra of 20,000 radio sources, better than 1 millijansky, and we detected 300 and 3,500 actually H1 absorbers. We also have gotten some OH detections as well, like about dozen of them, because those lines, OH lines, are much weaker, and also that kind of molecular gas is much rarer. So that explains the smaller number of OH detections. Prior to the survey, actually only a few hundred detections were known in the galaxy. So like this is like a factor of several increase here that we are looking at, and these spectra and catalogs are recently public, and I am already aware of that. Like there are some of the student projects in South Africa as well being carried out, and this is something which can be of interest to people here as well, and they can actually go to Mal's website, and uh, there is a very nice interface which you can use actually to explore images of radio continuum, these different spectra, and once you know what you want, actually you can download. And if you're only interested in doing a large scale statistical science, then the catalogs as are also available, and also you can download various continuum images in bulk as well from our website. So here I am showing some of the explorations that we have done of testing how the H1 column density is evolving as a function of visual extinction and H1 column density. And this is still referring to our own galaxy as well. And this is like, since within a pointing, we have not just one, but multiple sight lines, we can actually ask a question that if I see a certain strength of absorption towards one sight line, then how, whether within a parsec or two, another sight line shows structure at the same scale or not, because then that would be giving me important information about what are the sizes of these absorbing clouds, and that's very important information that can be then used to understand what sort of physical processes that may have undergone in generating these structures, these cold glass cloud structures in the ISM, whether this is related to turbulence as it is generally believed, or maybe something more is happening. So that's the base. So this is also uh, kind of exploration that can be done. And for this, like one can, one knows that like at optical wavelength, for example, we could use spectra of stars or spectra of distant quasars to look for gas in our own galaxy. One can potentially combine these to actually do a, 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 an independent exploration of the structure or the inhomogeneities that exist in the ISM here. So this is also could be of interest to PL. And so this is now I'm moving into the kind of work in progress, and also talking about some of the data releases that will happen later in this year, in the coming years. Still, I'm talking about L band because UHF band observation started about 18 months after the L band was completed. So as a result of that, there's a natural lag or a staggering of how L and UHF band science is being done, and those data releases are happening. So this is talking about now some of the extragalactic H1 absorbers. This is the spectral lines over a shift range of 0 to 0.6 that we are looking at, and using these, we are now working to constrain how the CNM or cold neutral medium fraction around the galaxies may be evolving. And this is what now ties back to the big question that I was describing earlier in my presentation, that our eventual goal is to measure the CNM covering factor of gas around galaxies as a function of redshift, and then connect it to the evolution of the star formation rate density. So this is now showing for the L band, and then our goal will be to do this generate these kind of detect these kind of spectral lines at different redshift range, and make this measurement over the entire band up to redshift of 2. At the same time, since we have so many spectra, we can actually stack them. This is one, and detect weak H1 emission at higher redshifts, something that is not detectable in galaxies at beyond local volume. But now MeerKAT is through the different surveys like MIGHTY, for example, is detecting H1 emission in galaxies at redshift of 0.3, 0.4. The question that we are asking here is that even though we don't detect H1 in galaxies directly through 21 centimeter line, can we stack a certain population of galaxies and from them determine like what is the H1 content of them, right? Because uh, the measurements of total H1 content and what we get from absorption go hand in hand in interpreting how the cold gas may be evolving. Because when we look at a 21 centimeter line in emission, that gives me a measure of total H1 corresponding to both cold and warm component. But when we look at it in absorption, we are looking at only the cold phase of it, right? So when we have both the measurements together, then we can really say that what is the fraction of cold gas now and how it is evolving, right? So it's a total budget that we can determine. So here we have got an independent measure detection from MALS itself of uh, galaxies at redshift of zero point 0.4. So you can see like combining this with absorption, we can now actually infer the budget of cold gas in and around galaxies that I was talking about. So this is nearing my concluding slide. This is the I have given you an overview of MeerKAT Absorption Line Survey. I have described you that through this large absorption line project, we are going to observe a number of cyclones that correspond to a redshift path, which is 1,000 to 10,000 times more than that has been done over last 2 or 3 decades with various surveys and telescopes. That's why it will provide a step ahead in understanding of cold gas in and around galaxies. And it's also a very competitive H1 emission radio continuum survey that I have demonstrated through some of the individual measurements and also the data releases. And there are 3 data releases that have already happened, which are available for public, and about half a dozen will happen over next few years, corresponding to L as well as UHF band, and that will also all be public. We will also release calibrated visibility data so that people can just do various imaging and non-imaging experiments with these to do a wide range of science. And this is my last summary slide, showcasing here like different kind of science that is possible with this kind of wideband data that we are obtaining. And this is all thanks to the excellent performance of the telescope and also its excellent sensitivity. So thanks a lot. I'll stop here, and here we can now discuss that what more that can be done. Happy to take questions. Thanks a lot.
Hey, thank you so much. It was great work and great talk. Thank you. Let's see if anyone has any question. You can either unmute or raise your hands. Okay, I see Ross has a question.
Hi, Neeraj. Thanks for the
Hi.
great talk.
Thank you.
I was wondering if it's a challenge because your pointings are spread all over the sky, having multi-wavelength data and spectroscopy in all those different regions. So you did talk about how some of the upcoming surveys will help with the spectroscopy. Whereas thinking for your stack that you showed at the end there, for example, do you have how many galaxies went into that stack, and do you have the data to be able to make a selection of star-forming galaxies, for example?
Yeah, so that's an excellent question, and that's something which we are planning in different stages. First thing was like when we wanted to do target selection, we got spectra with SALT for about these 300 objects, and that was a very good start. But now, when we are talking about these different pointings, we are talking about ability to get spectra which are of the order of tens of thousands, kind of thing, for it to become meaningful. So uh, the kind of stack that I showed in one of my slides is coming from just 12 pointings that overlap with Curb's survey. And as part of that survey, they have used Magellan and some of the other telescopes to obtain optical spectra of about 6,000 galaxies. So that's the number of galaxies going into that stack. And it shows that like just with few thousand of galaxies, if we can get spectra, we can do such nice stuff, right? Straight away.
Yeah.
One of the things that we are trying is to get a lot of spectra using Foremost. So so Foremost surveys will start early next year. So we have like 30 to 40% of pointings overlapping with different Foremost surveys. So some spectra would come from there. But I think Foremost would be getting like spectra sources maybe up to 19th or 20th of magnitude. And in some cases, like some of the AGN surveys would target even fainter sources as well. But there's a lot of room for identifying different pointings which can have sweet spot for different kinds of signs or different populations of sources. Because what we are as part of the continuum science, for example, what we will be delivering here through MALS is that like a few million radio sources detected down to, let's say, about 10, 20 microjanskis, and having very nice spectral indices as well, information, right? Because there are continuum surveys which may go really very deep in small parts of the sky, but then they would not have these many, like that 30, 40, 50 microjansky kind of sources, which are sort of, so it's an intermediate sensitivity continuum survey in that sense. And so it's covering a radio source population which is different. I think there are about 50 to 100 maybe clusters of galaxies in these different pointings. So if people are interested in those cluster related science, that can be targeted. We can look for groups of galaxies, for example, and do continuum or some other spectral line science. So through this publicly available data, I think, and identifying some of the interesting pointings starting from here, one can actually build various projects which may use like few pointings, go and follow up with SALT, for example, or start using photometry that is becoming available with decals or LSST, or then start using Foremost spectra or DESI spectra, which are becoming available as well.
Yeah, it's an amazing data set.
Hey, I see Uni Krishnan, if I'm not mistaken.
Hello, can you hear me?
Yes, please go
Hi,
ahead.
hi there. Thanks for the great talk. So I was curious about the automated pipeline that you mentioned for the data processing. So how automated is it in the sense that you do till 2GC and then because you will need to individually look at pointings and then proceed to the if you have right source contaminations and all, right? So how automated is your pipeline till what
So
stage?
what we do is that at this point, we do mostly 2GC, and that is actually completely automated. We don't really we have to just do diagnostics at one stage, which is after calibration, because imaging is the most compute intensive task. So we do a diagnostic step, which is like a visual check by someone to ensure that the calibration has worked. And after that, then all the imaging which uses generating imaging masks and self-calibration and everything, all that is completely automated and just runs on tens of pointings and through these different cycles over days and all and everything. So that does not require any intervention at all. And so these first data releases that has happened, they do show some artifact around uh, brightest of sources away from the pointing center. But then most of the images are actually clean actually, and there is no issue as such. And a lot of the science that can already be done with these. What we are going to do is that later this year start incorporating direction dependent corrections into this, and that would be then an additional data release that will happen maybe later next year for L band, and then the following year on UHF. We are going to use some slightly different set of algorithms that are generally used in terms of peeling. We are going to apply for these corrections in the visibility plane itself, and that's the reason we are doing it in these different steps, because some of these algorithms are still in development stages. So we wanted to first go do everything basically that is possible with the standard approach, define this baseline down to say 10, 20 macrojanskeys, and then apply these new algorithms and then ask the question, right, that whether this is really evolving, improving or not, or introducing any bias into the correction, because because all these different what we call a 3GC or direction dependent correction based algorithms, these are like new. Some of them make look image better, but not necessarily we know always that the measurement that we are making is actually correct or not, or like how much systematic error has been introduced into it. So these are some of the questions that we will start investigating and incorporate this in our subsequent releases.
Yeah, thank you.
But just to enable that, we are not imposing any particular method on the community. We are going to release these with calibrated visibilities as well later this year. So if someone wants to sort of try, and that's the idea actually, right, of releasing everything like that, people use them the way they like. And then we learn from that as well that, okay, that one was better, and then we can incorporate that too.
Yes, absolutely. Thank you.
Yeah.
Hi. I would like to ask you, when you do cross correlations between AV and say the OH and the H in the interstellar medium, where does those AVs come from?
So these are coming from far infrared data, all
So
sky
it's
maps of the galaxy. Yeah. Yes.
So it's dust emission essentially.
The dust emission, yes.
Yeah. Okay, thank you.
And H1 emission that I showed, that was coming from Hi4Pi survey.
Yeah, okay.
And there's a detailed absorption line catalog coming from MALS of these 20,000 satellites, which is available at our website. So detailed explorations are possible on that. We have only done first order things. And some of this exploration intention was to really not just make a data release, which is sort of then people have to first understand that how good that is. So I explained 3 data releases. In each data release, we have done at least one exploration which is down to the limit of the project or the sensitivity of the survey. So that like when you are looking at the data release paper, you get a good idea of like, okay, up to this level, I can trust this. This is the level at which I start getting false detections, for example. This is the completeness, or this is how, or this is like a fruitful direction for me to take. And whereas this is the direction in which if I go, I hit the limit too soon. So that's the kind of exploration we have done along with every data release.
Thanks.
All right. I just have a very basic question. So in the science cases that you were showing, the one at the higher redshift, 1.3 redshift, so you said that there is nothing shown, no emission line in the optical spectrum, but
no absorption line.
No absorption line. Okay,
Right.
okay. So there are emission lines, because I was just wondering about the verification of how we are sure that it's a quasar. Is it only through the radio emission, or we see also the emission lines in the optical?
Yes, so there are quasar emission lines from which we measure its redshift. The general expectation is that it's a quasar, and radio emission is also beamed. So we would expect that if I detect a certain amount of gas in radio, I would expect it to detect it in optical as well. But and that's often the case. But in this case, it turns out that it's completely escaped. This is interesting for all of us who have been doing this multi-wavelength spectroscopy for last several decades, right? Because radio spectroscopy for all this time has been driven by optical surveys, right? You get a redshift, you know where to look at, and then you tune your small radio band to that spectral line and do your exploration, right? That's how radio spectroscopy has been done. So always we detected something at radio and then followed it up in optical, sorry, in radio, right? It's now for the first time that we don't have to depend on optical, right? We just take these large number of radio spectra. So we can now actually truly ask this question that if we detect something at radio, is there something at optical or not? So like before MeerKAT surveys, we would not have observed this source at all because you will look at the optical spectra, nothing is there, and if you don't decide, TAC will decide it for you that it's not a good project to do because there's nothing in the optical. You will not be able to observe this sight line, right?
Yeah.
But here, like when you don't do anything, just let the instruments speak, you get something which is totally new, and that then lets you ask a more general question that do AGN have much more cold gas that we may have missed in our statistics determined from the optical absorption line studies, right? That's the question that we can ask now.
Yeah, definitely. Okay, if there's no more questions, thank you so much. It was a great talk, and thank you everyone for joining today, and we'll see you all in the next colloquium.
Well, thank you so much for inviting me, and you can reach me by email. I'm happy to talk over Zoom or anything. Do explore our data releases, and if there's anything there that is not there but you need it, feel free to
Thanks.
contact.
Bye.
Thank you.
Bye.
Thank you. Bye.